Hello everybody. In this video we'll learn about matrix operations. Up to this point we have spent a lot of time focusing on 2x2 matrices, and we'll talk about how to do operations on matrices of different sizes in this video. So to begin, we need a way to talk about the size of a matrix, and so we say an m by n matrix, or an m times n matrix, has m rows, so those are horizontal, and n columns, those are vertical. And we can also think of vectors as kind of a special case of a matrix. A vector is an m by 1 matrix. It's just a single column. Now, for 2x2 matrices, we know how to do lots of different operations. In these videos, we've discussed the matrix vector product. We've talked about matrix multiplication. We've even gently referenced scalar multiplication very informally. That's when you take a constant and you multiply it by all the entries of a matrix, like so. And that was briefly mentioned in the context of inverses. When we calculated the inverse of a 2x2 matrix, we had noted that each term had the same denominator, and so we factored that out, alluding to scalar multiplication. Furthermore, even though we might not use it as much as these other operations, we can also define matrix addition. So if you have two 2x2 matrices, then you can define matrix addition as just adding together the components that occur in the same locations. So the sum of two 2x2 matrices is another 2x2 matrix. And this will become useful in a few cases in future videos. Now, to talk about matrix multiplication, first we'll talk about vector matrix products. And so we'd first like to recall that a long time ago, when we first started talking about this topic, we spent some time discussing how to convert between systems of equations, vector equations, and matrix equations. Because that gives us different ways to represent the same concept, the same equation, this would very naturally lead us to define a matrix vector product in ways such as this. And so you might imagine we have, for instance, the left-hand side of a matrix equation. We have a coefficient matrix times a vector of variables. Well, that should be equal to this expression right here. In particular, note here, we have a 2x3 matrix. There are 2 rows and 3 columns. And a 2x3 matrix times a vector with 3 components gives us a vector with 2 components. Similarly, we could discuss a matrix equation where the left side has a 3x3 coefficient matrix times a vector with 3 components, in which case you would get this result. And in both cases we see this dot product-like calculation occurring for each of the components, and in each case we think of taking the coefficient matrix and partitioning it into row vectors, which are then dotted with this vector of variables. As a completely numeric example, let's say we had the matrix 2, 1, 5, 6, 3, 4 times the vector 7, 2, 3. Well, to calculate that product, we'd first take this first row, dot with this column. We get 2 times 7 plus 1 times 2 plus 5 times 3. That gives us 31. For the next component, we take the second row, dot with this column vector. We get 6 times 7 plus 3 times 2 plus 4 times 3. When we add those up, we get 60. So this matrix times this vector gives us the vector 31, 60. And that's how we can define matrix vector products for matrices of different sizes. However, we do have to be a little bit careful. For example, let's take a look at something like this. What if you have a 2x2 matrix multiplied by a vector with 3 components. Well, in this case, this can't be calculated. It doesn't make sense. Or as we often say in mathematics, it is undefined. Because if we go through our normal process and partition the coefficient matrix into rows, and then if we try to do the dot product of this row with this column, we have 2 vectors of different sizes. This row has 2 elements. This column has 3 elements. So we cannot calculate the dot product in this case. And there are not enough coefficients, there's not enough columns in this matrix for these variables. So this leads us to the following observation. If we're given a matrix A and a vector V, the matrix vector product A times V is defined, or it can be calculated, only when the number of columns of the matrix is equal to the number of rows of the vector. Or if you think about it this way, if your matrix is an m by n, then your vector, to be compatible with multiplication, must be n by 1. Right? These 2 inner components must be the same. And the result will actually be an m by 1 vector. Right? Before, we saw that we had a 2 by 3 matrix times a 3 by 1 vector, and the result was a 2 by 1 vector. And that will generally be true. Also, we'd like to talk about matrix multiplication for matrices of different sizes. So, to begin, let's recall that repeated matrix vector products were used to define matrix multiplication. Originally, we asked ourselves this question. Right? If we had a calculation like this one on the left of this equation, which within the parentheses we first calculate a matrix vector product, that gives us a vector, and then we'll multiply it by this matrix on the outside, would it be possible to first somehow combine these 2 matrices and then do our matrix vector product? Right? What would this product have to be defined as in order to make these 2 sides equal? And we learned that the calculation that we need to do, so we'll take this first matrix and we'll partition that into rows. We'll take the second matrix and we'll partition that into columns. So we can think of that first matrix as having row 1 and row 2. The second matrix as having column 1 and column 2. And then the matrix product is calculated using dot products of these rows and columns, as seen here. And as we will see, we can define general matrix multiplication in a similar way. It's completely analogous. But before we talk about that, just as a brief aside, when these matrices get larger, we quickly run out of variables. So occasionally we will use something called double subscript notation. So for example, the elements of a matrix A, we might write in this format. Right? The matrix itself, we usually use a capital letter. The entries in the matrix will use the lowercase version of that letter. And the way we would read these numbers, we'd read them as 2 separate numbers. So this is A11, A12, A21, and A22. Right? Not A11, A11. And similarly for B and C, we would label the entries as so. In general, given a P by Q matrix M, M sub ij refers to the entry in row I and column j. And here I ranges between 1 and P, the number of rows, and j ranges between 1 and Q, the number of columns. Right, so for example, C23 in this matrix occurs in row 2 and column 3. Right, and in here, mathematics, we start counting with the number 1. I point that out because sometimes in computer science we would start counting with the number 0, but not in mathematics. All right, so that notation will be useful in what follows. So for an example of how we would define general matrix multiplication, what if we had a 2 by 2 matrix times a 2 by 3 matrix? We'd follow a very similar process. The first matrix we always partition into rows. The second matrix we always partition into columns. So that first matrix has 2 rows. The second matrix has 3 columns. And then to calculate the product, we would calculate the dot product of these rows with these columns. And the result would be like so. In this case, right, these dot products make sense because the rows have 2 elements and the columns in the second matrix have 2 elements. Right, so these dot product relations are well defined. One interesting thing about this example is that even though we can calculate the product of the matrices in this way, if you try to reverse the order of these 2 particular matrices, the result is undefined, and here's why. At first, it might seem that everything's okay, because surely you can partition that first matrix into rows, and you can partition the second matrix into columns. You have a result like so. But once again, when you try to calculate those dot products, the rows of the first matrix have 3 entries, but the columns of the second matrix have 2 entries. So we can't calculate dot products in this case. So we would say that this product is undefined. In general, given 2 matrices, let's say that capital A is an M by N matrix, and capital B is a P by Q matrix, the product A times B, matrix multiplication, is defined only when N equals P. These 2 have to be the same, and the result will be an M by Q matrix. N and P must be the same, so you can calculate those dot products. And since you have M rows in the first matrix and Q columns in the second, the grid of cross products will have M rows and Q columns, leaving us with a result of this size. So, as a collection of examples, before we even get into calculating the actual entries, here are some examples of when matrix multiplication is defined and what the size of the result will be. So let's assume that matrix A is 2 by 2, matrix B is 2 by 3, matrix C is 3 by 2, and matrix D is 3 by 3. Then A times B will be a 2 by 3 matrix, if those are compatible, but B times A is undefined. We just saw that example on the previous slide. Right? We can't multiply a 2 by 3 times a 2 by 2. We can multiply a 2 by 3 times a 3 by 2 because those inner dimensions match, and the result will be a 2 by 2 matrix. Meanwhile, if you reverse the order of B and C, in this case, it's still defined, and you get a different size matrix. Right? If you multiply C times B, right, C comes first, so this 2 matches that 2, so the dot products are compatible, and the result is 3 by 3. If you try to multiply C times D, the result is undefined. Those are incompatible sizes. But D times C is all right. The result then would be a 3 by 2 matrix. And finally, sometimes you can multiply a matrix by itself and sometimes you can't. For example, if A is a 2 by 2 matrix, A times A will also be 2 by 2. If B is a 2 by 3 matrix, then B times B is undefined. So now let's look at some examples of actually doing the calculations. So here we have a 2 by 2 matrix multiplied by a 2 by 3 matrix. Right, to calculate this, let's partition the first matrix into rows, the second matrix into columns, and calculate some dot products. So we have 2 times 7 plus 1 times 6. Then we have 2 times 9 plus 1 times 8. We have 2 times 5 plus 1 times 0. Then in the next row, we'll have 3 times 7 plus 4 times 6. We'll have 3 times 9 plus 4 times 8. And 3 times 5 plus 4 times 0. When you calculate those up, you'll get the matrix 20, 26, 10, 45, 59, 15. Right, so very similar types of calculations as when we worked with 2 by 2 matrices. There are just more calculations. Here we have another example of a 2 by 3 matrix. Right, so we have 2 rows in that first matrix, 2 columns in the second matrix. So the result will be a 2 by 2 matrix. I won't read this all out to you. It's not that interesting, but you're welcome to pause the video and take a look and see how those calculations line up. Finally, one more example. This is about as large of a matrix multiplication as we're ever going to need to do in this course. Here we have a 3 by 3 matrix times another 3 by 3 matrix. Partition that first matrix into rows, partition the second matrix into columns, and then we've got a total of 9 dot products to calculate for those 9 entries, and the result is another 3 by 3 matrix. Just as some ending notes, and hopefully this material is not too bad, not too different from what we've been doing before. We didn't really talk about scalar multiplication on arbitrary sized matrices, but scalar multiplication will always be defined. You can always multiply all the entries in a matrix by a single constant. So we can always do that. Matrix addition, however, can only be defined when the 2 matrices have the exact same size. So they have to both have the same number of rows, and they both have to have the same number of columns. And so, things to think about, because in future videos we will continue doing scalar multiplication and vector addition as well. And for now, I'll leave you with this. As I always say, you learn math by doing math. So I'd like you to go ahead and calculate this matrix multiplication. Here we have a 3 by 2 matrix times a 2 by 3 matrix. We know that's compatible because these dimensions match. As always, you'll want to partition the first into rows, the second into columns. The resulting matrix, how big will that be? And then calculate that out. All right, good luck with that, and thanks for watching.